is not quite yet. But this, are you muted yet? Put your hand up your phone.
Luis, are you on a speakerphone? Can you pick up a handset if you have one? I'm not hearing your audio right now. Double check to make sure you're not muted. Are you dialed into the telecom line? Okay, we'll wait for you to dial back in.
Sorry, everyone. Just hang on for a couple more minutes. I think we're about to get this right. It is ironic that the one we're having trouble with is just right across the way here at Ames.
Can you hear me now?
Yes. Yes, we have you now.
Okay. I'm going to be speaking about an effort of understanding what the two neutron detectors mapping or that they've been mapping the polar regions of the moon. As everyone knows, for quite a while, people have been publishing some papers which have some doubt on the interpretation that the LAND team has got about its own data. So I thought it would be time to use some statistics which allow put both data sets on equal ground and draw the proper conclusions about such data sets.
You can just use the arrow keys at the bottom there.
Right. Oh, okay. Excellent. So the first step in our talk is to introduce the concept of contrast field and try to explain pedagogically what are the different phases of the detection in the neutron detectors. Then we'll move on to use the two statistics that are widely used in other fields to quantify things like point spread function, smoothing, noise level, different levels of backgrounds, and so on. And I will apply this to some synthetic data, since we can control the experiment, and then I will apply those very same statistics to real data. And at the very end, we will draw the conclusions. So let's say that we have a mock South Pole count rate map, but rather than using the usual count rate, you just divide the count rate by the mean and subtract 1. And this is called, in these other fields in physics, industrial physics, contrast. So the next step that we are going to introduce is, let's say, introduce the point spread function. And as we can see, most of the detail appears on small scales, while on large scales, things pretty much agree with the previous map. So next, we introduce a background, and I would say the detail has gone. And on the top of the background and the point spread function, one adds the noise. And these are the 4 different fields that I will use to quantify the autocorrelation function in the power sense. So how do they look like? Like when we use the statistics on the truth. So before going there, it's worth it to spend a few minutes looking at the definitions, what the 2-point correlation functions are. Basically the product of the contrast field at 2 different locations, separate by a distance r. The power spectra is the Fourier transform of that very same variable. So basically, encapsulates the same information, but that can be, how can I say, visualized in a different way. So this is the 2-point correlation function, or autocorrelation function, for the first map that we saw. So basically, we can see fluctuations throughout a whole range of scales. So once we introduce the point spread function, one expects that on small scales, we remove what you see in this map, while on large scales, the autocorrelation function is going to be something similar. For instance, when one introduces a point spread function of 45 kilometers, similar to what Lunar prospector does, one would see something quite like this. So the next step would be to add a background. So rather than changing the autocorrelation function, the amplitude moves downwards. Eventually, you add noise on the top of the 2 previous steps, and that's the measurement that you get. Yet for a particular realization, and the error bars you can see around those values, are basically computed over 100 different realizations of the noise. The power spectra looks like this. So starting off from a full line of what we call the truth, once you smooth, we clearly see that we wipe out power on small scales. I beg your pardon. So on small scales, in this plot is on the right-hand side. So as in the previous statistics, once you introduce the background, one goes from the dashed line into the dotted line, and it goes downwards. So the next step is to add noise. And you clearly see that for small scales, the power spectra flattens off. So we are learning out of this exercise that we can quantify the scales at which the noise dominates the signal. Right. So after this exercise, we think we understand how these two different estimators work. So let's have a look to the real data. So, but before coming there, we are going to apply these two estimators to two different data sets. So we have a subset that we are going to call out high altitude lunar prospector, the orbit of which is roughly 100 kilometers, and the spacecraft was there for roughly 1 year, and the full with half Mach is roughly 130 kilometers. Then we have the low altitude, or orbit is around 30 kilometers, that lasted for 7 months, and full width half max is 45 kilometers. And then we will use length collimated data out of an orbit that is roughly 50 kilometers, and as far as I'm aware, it's been there for 21 months. And the question mark there is a little bit of a provocation, shall I say, because I think we can measure that very same amount out of our statistics. So even before going, we should show what the maps for the what can I say, that we are going to put through the estimator. And we are presenting the lunar prospector, and clearly we can see cabeos, and we also can see some other signal on the right-hand side of the shoemaker and so on. Now, the same map for land, I think it's fair to say you still see the same two big fixtures, cabeos on the top left and shoemaker off the center toward the right side. So the two-point correlation function looks like this. So the very top one is the lunar prospector, low altitude. The second from the top is the lunar prospector at high altitude orbit. And the one at the very bottom, or the lowest, is the land collimated data. So what we are learning out of this is that somehow the autocorrelation function can be, there are two fundamental parameters. One is shape, and one is the shape, another is the amplitude. And the two bottom ones are rather similar in shape, and they are very different of the low altitude lunar prospector. So what we know about the lunar prospector is that point spread function is roughly 130 kilometers for the high, I beg your pardon, altitude, and it's roughly 45 for the low altitude.
Louis, you have 2 minutes left.
Okay, no problem. So it's fair to say that just out of the shape of the autocorrelation function, it seems that the land point spread function looks more like the high altitude lunar perspective than anything else. So going. So what can we do with the land? Can we actually correct? And the truth is, out of the Eke tool in 2012, we found that the fraction of the thing that is in background is 0.54. So that means that we can rescale the 2-point current correction function and find what happens. And the result is exactly that. It seems exactly similar to the altitude, the lower perspective, high altitude. Oops. So, but how does it look, the correct field, the contrasted field? It looks exactly like this. It's considerably noisier because you have removed a background. So the power spectrum applied to that field looks like this. So on large scales they look very alike, all the three, but on small scales the land data is dominated by noise. So, and the conclusions are up. I will end up right here.
All right, we've got a few questions. First, Richard Miller says, Louis, have you performed the same correlation analysis on the LEND SETN uncollimated data set as a further validation of the approach? If so, does it show the appropriate trend given the lower orbit altitude?
So I couldn't understand you.
Okay, have you performed the same correlation analysis on the uncollimated SETN data set as a further validation of your approach? If so, does it show the appropriate trend given the lower orbit altitude? Given the lower altitude orbit?
No, yeah, it's correct. So the two trends in the correlation function are different.
Okay. Gordon Chin sends in a comment, sends in a question. Tim McClanahan earlier showed the neutron suppression of epithermal neutrons at Shoemaker Crater by Bill Boynton that is closely aligned with and very much within the Lola topography that defines the crater. Wouldn't you agree that this 10 sigma result taken by the collimated LEND detector can only be obtained by an instrument having high spatial resolution in contrast to your contention here?
No, do you know why? Because we have done that very same exercise. And what you see in their data, in their maps, is basically the smoothing that they have applied. Their smoothing is variable in latitude. And if you look at this very same map that we produced, which is very similar to what Boynton et al. Produced, it's very different of the one that I'm using to compute the autocorrelation function. And that's due to the fact that they've smoothed the map.
Yeah. Gordon here says smoothing can only degrade resolution, not enhance spatial resolution.
No, but you are not in. What I'm saying is, look at look at this map. Shoemaker is there. I'm disputing that it is not.
Well, I think what Gordon's saying is that the Shoemaker edges are so, I mean, the change in neutron count in the slope and the slope in the topography are so closely correlated. Hard to imagine that was just a fluke.
Look, I'm not saying it's a fluke or not. I'm not even disputing that there is not hydrogen there. What I'm saying is I'm doing a measurement with 50,000 pairs, and I get 2-point correlation function. While they pick a pixel and claim that they can see, they have high resolution. So I suspect that my result is far more robust than theirs.
All right, Richard Miller has a comment. The statistical approach using that Shoemaker analysis underestimates the uncertainty in the background. Okay. So.
Well, I don't want to go into such an analysis, but it could well be.
All right. Yeah, I think that's it for the questions.